In the previous slides, we have learned how the effect or how temperature change and pressure change affecting the lower flammability limit and the upper flammability limit. In this slide, we will discuss what we call flammability limit of mixture, which means that I'm talking on cases that has two or more than one component. You have a mixture. Let's say that you have a mixture of gas stream. So let's say you have gas stream, and this gas stream has component 1, component 2, component 3. Let's say that component 1 is methane, component 2 is ethane, component 3 is propane. And let's say that I know how much is the mole fraction. Let's say that this is 0.3, 0.2, 0.5, and I know how much is the lower flammability limit for each component. So let's say it's number here, number here, number here, and I know also the upper flammability limit for each component as well. So now I need to calculate how much is the lower or the flammability limit for this mixture that has the 3 components, 1, 2, 3. So I'm gonna follow what we call Le Chatelier rule, where Le Chatelier rule stating that the lower flammability limit for a mixture equal to 1 divided by the summation of the mole fraction of that component in the gaseous phase divided by the lower flammability limit for this specific component, which means that if I want to find the lower flammability limit for this mixture that has 1, 2, 3 components, so it's going to be 1 divided by, so my lower flammability limit for this example will be 1 divided by 0.3 divided by the lower flammability limit for, let's say, methane. Let's say that I know how much is the lower flammability limit. Let's me call it X value, plus 0.2 divided by the lower flammability limit for ethane, which is, let me say it Y, another value Y, plus lower the mole fraction, which is 0.5 divided by the lower flammability, let's call it Z, the value. So I'm going to say that I have here the lower flammability limit X, Y, and Z. So this way I find how much is the lower flammability limit for this mixture that I have. And the same rule apply also when I calculate, for example, how much is the upper flammability limit, where I use the Y fraction or the mole fraction for that specific component in the gaseous phase, and I know how much is the upper flammability limit for this specific compound. Okay, but there is one thing that I need to keep in mind, which is this hint or this point. Okay, that always Y is normally based on the combustible basis, which means that if I have a stream that have three components, 2 of them are flammable or combustible and 1 of them is not combustible. So let's say that I have a gas stream that has, for example, again another example, let's say that I have component 1, which is, for example, methane, component 2 that is ethane, and component 3 that's nitrogen. Okay, and I know that the mole fraction, let's assume that I have, for example, number of moles. Let's say that I'm talking about number of moles. Number of moles 1, number of moles 2, number of moles, for example, is 5. So now when I calculate Y, so Yi, the one that I'm going to calculate, will be based on the combustible fraction. Nitrogen is not combustible, so it's going to be out of your equation. So I'm going to assume that I have the total of these 2 components. So total number of mole is 3, which means that Yi for methane will be equal to 1 divided by 3. And Yi for ethane will be 2 divided by 3. And this has 0 value because nitrogen compound, so this is for this, this is for this, this is for this. So Yi, where the mole, Yi is the mole fraction for methane will be 1 divided by 3, where I take the total number of moles, 1 plus 2, which is 3 mole, which are the components that are combustible or flammable. and nitrogen will be as a result excluded. So that's how we calculate always yi. So this is very important to mention, that yi will be always based on the combustible fraction or the combustible basis. Means that I calculate how much is the number of moles, or how much is the percentage of that mole or the percentage of that component in the gaseous phase, for example, for this combustible material only. Now in this slide we will discuss what we call estimating flammability using some empirical formula, where you can estimate the flammability limit or the flammability region for hydrocarbons in general using these formulas, where lower flammability limit and upper flammability limit can be found as a function of something called CST, where CST stands for the stoichiometric constant, which is a volume percentage, or CST. Then CST is what we call stoichiometric concentration, or the volume percent concentration, or stoichiometric concentration. And you can use these two formula for lower flammability limit and upper flammability limit as well. But now the question is, how do we calculate the CST, where CST can be calculated based on this formula, where CST, or the stoichiometric concentration in volume percent, equal to 21%, which is the percentage of oxygen in air, divided by 0.21 plus Z, where Z is the moles of oxygen per mole of fuel, which means that I'm mimicking or I'm modeling the example of combustion or oxidizing a fuel based on this equation. If you have a fuel which is CXO that has this formula, and you are oxidizing this chemical or this fuel with oxygen to get, for example, and you know that this is like a classical oxidation reaction, you will get CO2 and H2O, and you know from the balance of the equation how you can balance this from the basic fundamental point of view. How do we balance this equation? Therefore you can find Z after balancing the equation, that Z will be always the moles of oxygen per mole of fuel, that which means that this is the mole of oxygen required to burn the fuel that you have, or the quantity of fuel that you have. And this is normally you get it from the balance of the equation. So you have two options: whether you balance the equation and you get Z directly, or if you forget how to balance the equation and you don't want to go through this, you can use this formula, where Z equal M, where M is the number of carbon, for example, atoms in the fuel compound, okay, plus 1 over 4 X, where X is the number of hydrogen atoms, for example, how many hydrogen you have in that compound, minus half Y, where Y stands for the number of oxygen of that compound. So if I'm talking, for example, about CH4, as a result for CH4, M equal 1, X equal 4, and Y equal 0. Okay, so you can simply find how much is Z. As a result, Z will be 1 plus, and as a result Z will be 1 plus 1 over 4 multiplied by 4, which is 1 plus 1 equal to 2. Therefore each 1 mole of CH4 will require 2 mole of oxygen to be combusted, or to be oxidized completely, to give you carbon dioxide and H2O as well. So this is how you calculate CST. And as I mentioned earlier several times, these formulas, these are like, you can have them in your exam, or I will provide it for you in the exam, so you don't have to memorize them, most of these formulas. If you need further details about the CST, which is the stoichiometric concentration volume percent, you can also use this formula as well. And this is the derivative, how you obtain it. But I'm not going to ask you about the derivative. Only you need to know that this is how you calculate CST, which is very similar to the previous one, where it's 100 divided by 1 plus Z over. So you calculate Z, and this is, in fact, this is like more simple equation that you can use. You can calculate Z and directly divide Z by 0.21, add it to 1, and all divide 100 by this number, and that's it. You get how much is the CST in the, which is the volume percentage. We're going to look now at this exercise straightforward application. for the formulas that we have seen. You need to calculate or estimate the lower flammability limit and the upper flammability limit for hexane and compare the calculated limit to the actual values. So you have the hexane, and you know that hexane is C6H14. So directly the first thing we're gonna do is that we need to calculate lower flammability limit and upper flammability limit for hexane, and you have to keep in mind that hexane is hydrocarbons, means that I can simply use the formulas that we have learned before, which is lower flammability limit and upper flammability limit as a function of the stoichiometric concentration. And you can simply find this by writing first the equation of the oxidation equation for the hexane, where C6H14 plus oxygen will give you CO2 and H2O. And now I'm gonna balance the equation. So you have two options to balance the equation: whether you follow the previous equation that we have seen to calculate how much is Z exactly, or you can just simply balance the equation, and from the balance you get how much is the Z value for that equation. Okay, so if you balance this equation, now I need to get how much, you know, this is C6H14, and if you still remember, this one is M and this one is X, and Y will be equal 0 in this case. Okay, so Y will be equal 0 in this case. Therefore you can simply calculate how much is the, or how is the Z value based on that equation, where Z equal to M plus 1 over 4 multiplied by 14 to get how much is the exact value, where, and then you get Z to be equal 9.5, and by applying that equation, which is 100 divided by 1 plus Z divided by 0.21, you get how much is the exact value of the CST. And once you get the value for the CST, you can simply calculate how much is the lower flammability limit and the upper flammability limit for this compound. Finally, if you want to estimate the LOC, which is the limiting oxygen concentration, for also hydrocarbons, you can get it as the same way, where LOC equal to the Z value multiplied by the lower flammability limit for that specific compound that you calculate. And normally, for most of the hydrocarbons, the typical values for LOC is in between 8 to 10%. You can use this value as a guideline, but normally it's better to do the calculation, because you calculate the Z from the balance as well of the equation, or from the equation that we have learned, where Z equal M plus 1 over 4 divided by X, where X is the coefficient or the number of hydrogen atoms in the fuel, M is the number of carbon atoms in the fuel, and Y is the number of oxygen molecules in the fuel. And then you calculate Z, and then you calculate how much is the LFL, and from that equation you can find how much is the LOC, or the limiting oxygen concentration. And as we mentioned, it's typically in the range between 8 to 10%.